Hello and welcome back to another Medmo Podcast, presented to you by Mohammed Mahmood. And in today's podcast we'll be focusing on magnetic resonance imaging, also known as MRI scanners. In just a few decades, the use of MRI scanners have grown tremendously. Doctors can order MRI scans to help diagnose things such as brain tumours, torn ligaments, cancer and strokes, and these are just to name a few. An MRI scan is the best way to be able to see inside the human body without having to cut it all open. So when going into an MRI scan, you're stripped off all the jewellery and credit cards and any other metallic objects which you are wearing, and you're asked detailed questions regarding all the metallic instruments you may have inside you. Then you're placed onto a tiny slab and pushed through a hole, which is hardly big enough for any average sized human. Then you're subjected to all these loud noises, you have to lie perfectly still, and they're going to do this to you over and over again. And as each moment passing by, you can't help but wonder what is happening to your body as you're going through this machine, and could it really be that this ordeal is truly better than any other imaging technique out there, such as X-rays and CT scans? And for us to really understand this, we need to look at how MRI scanners work. So MRI scanners do vary in size and shape, and some newer models have a greater degree of openness around the sides, but the basic design is the same, where a patient is pushed through into a tube that's roughly 60 centimeters in diameter. But what's going on inside there is the real question. Now, as it says in the name itself, magnets. That's the biggest part of an MRI system. And what's happening here is a horizontal tube, the same one which the patient enters through, and running through this is a magnet from front to back. And this tube is known as the bore. But this isn't just any other type of magnet. What we're dealing with here is an incredibly strong system, one which is capable of producing a large stable electromagnetic field. So just to recap, in a nutshell, an MRI scanner applies a very strong magnetic field, and how strong this is measured in Teslas, and it's roughly about 2 to 3 Teslas. And to really understand the scale of the magnetic field we're using here, we can compare it to, say, something as simple as a fridge magnet, which is 0.01 Tesla. So we're looking at roughly 1,000 times the strength of a typical fridge magnet. Now, most MRI systems use an electromagnet, as you may remember from GCSE as well. Electromagnets are made from coils or windings of a wire, and a current is passed through. Now, to create such a huge magnetic field, up to 2 to 3 Teslas, we're going to need to have a huge deal of energy, especially to maintain such a magnetic field. And to lower the cost down, you may remember, especially A-level students, something to do with superconductivity, reducing the resistance, and ensuring that we can maximise the biggest field we can get out by lowering the cost and lowering the use of energy. And we do this by taking the wire down using liquid helium. And we take this to something known as absolute zero, which is roughly minus 270 degrees, and is one of the closest points to absolute cold, should I say, we can reach. And this cold is insulated using a vacuum. And while superconductive magnets are extremely expensive, a strong electromagnetic field allows us to have the highest quality of imaging, and superconductivity keeps the system economical to operate efficiently. So now we know what exactly an MRI machine consists of, but how is it that these electromagnetic fields passing through our bodies then form some form of picture of places in our body? And the way this is done is an MRI machine takes pictures of places within your body which contain primarily water, and the detail on these images come from the ways that the tissues interfere and interact with the EM waves coming from the water molecules. Now, the concept and idea that water is releasing EM waves may seem pretty crazy, to be honest, and those of you who are A-level students would have looked into this already and how each object gives off its own wavelength as well. But to keep things simple, essentially all molecules are doing this all the time, and the signals that they are emitting are so tiny that you'd only be able to notice them if you went out looking for them. So an MRI is literally a device which first should I say, excites the water molecules and then causes them into releasing waves and records purely the location of where those waves are coming from at a high degree of accuracy. So as you know, your body is pretty much entirely made of water. Things such as blood vessels, lymph nodes, even solid bones are soaked with water molecules, each of which contain, as you should know, 2 hydrogen atoms, and at the centre of each hydrogen atom sits the nucleus, consisting a single proton. Now, we can see the proton here as a tiny bar magnet, with the north and south pole, just like the north and south poles of a needle on a compass, which tend to align with the magnetic poles of the Earth. In the presence of a strong magnetic field, each proton in the water twists its orientation so it's now aligned in the direction of the magnetic field. Now this is a lot of information, so just to recap, all that's happening is that we're firing a magnetic field into all the water molecules, so directly at the protons, and what these are doing, they're just simply changing their direction and aligning with the direction of the magnetic field. So now we've got all these protons aligned. So next what the MRI machine does is apply another wavelength, another frequency, a radio frequency pulse to be specific. And these are specific just to hydrogen. And the system will direct the pulse towards the area where we want to have our images taken and to examine. And when the pulse is applied, these protons will take in and absorb the energy and spin in a complete different direction. So now we've changed them once using the strong magnetic fields, and now we've changed the orientation again using the radio frequency pulse. But when this radio frequency pulse is turned off, the hydrogen protons slowly return to their natural alignment within the magnetic field, and as they're doing this, they're releasing all the energy that they had absorbed from the radio frequency pulses. And when they do this, they give off signals and wavelengths, and this is where the coils in the MRI system pick these up and send these to a computer system. So let's quickly recap. What's happening is that we're applying another wave, a radio wave should I say, through this, and the protons change their direction, and once the radio wave is gone, they return to their natural alignment, and this causes an excitement initially, and then a relaxation. And during this relaxation process, we're giving off another form of energy which is absorbed and picked up by the coils in the MRI system, and these are sent to a computer system. Now the computer receives these signals from all across the body of the spinning protons as mathematical data, and the data is converted into a picture. Now the imaging part of the MRI, that's moving more into an area of computing physics, which is for another podcast and another day. So now we've looked into how the MRI machine applies different types of energy and signals to form an image for us to analyze. However, again, why choose an MRI if it's such an expensive process, such a long process, compared to, say, something like an X-ray? Now, an X-ray is extremely effective for showing doctors a broken bone, but say if they want to look at the patient's soft tissue, such as organs, ligaments, and the circulatory system, they're likely wanting to use an MRI. And the reason for that is, as mentioned before, MRI's ability to image on any angle and plane. But for these high quality images to actually be produced, the patient can't move very much at all, and they have to stay still for such long periods, from 20 all the way to 90 minutes and even more. And the slightest movement of any part being scanned can cause distorted images, and that means having to repeat it all over again, and that's an even further high cost to the high quality imaging we're producing. And MRI systems themselves are extremely expensive, let alone running them. So many people also have a concern to the fact that, your atoms are being mixed about. But once you're out of a magnetic field, your body and its chemistry return back to normal. And there have been so far no known biological hazards to humans from being exposed to magnetic fields of the strength used in the MRI. The fact that MRI don't use something that you may remember from GCSE, ionizing radiation, which is extremely dangerous. It can actually cause cancer as well, and other imaging devices use this as well, whereas MRI doesn't. It's a real comfort for patients to know that they're not going in such a dangerous side effect area. And most facilities actually don't even use MRI as well in pregnant women, due to the limited research of biological effects of magnetic fields on developing fetuses. However, this doesn't mean we take MRIs lightly at all, and MRIs can become an extremely dangerous place if we don't put strict precautions and these are not observed. Things as mentioned before, credit cards or anything with magnetic encoding with them will be erased. Any metal objects within the area, within the room, in the scan room, could become extremely dangerous projectiles, and this literally means you could have things flying around. For example, paper clips, pens, keys, scissors, jewellery. I've got a huge list here of small objects which can be pulled out of pockets and off the body without any warning and fly at extremely high speeds towards you, and that's why loads of precautions are taken beforehand to ensure that the MRI suite and scan room is as safe as possible. However, overall, MRI scans do provide a real safe alternative to X-rays and CT scans due to not having any ionizing powers at all and creating high quality imaging without having to slice up the patients and being able to do that on various axes and angles. There are some setbacks in comfort and cost, however in the long run it's truly worth for a doctor to know what's happening inside your body. And that's essentially how an MRI scanner works, and the setbacks and the advantages of them. I hope you enjoyed this podcast today, and I've been your host, Mohammed Mahmood. Thank you for listening.